Welcome to an introduction to AI safety, ethics, and society. In this lecture, I'll speak about safety engineering. In trying to get oriented in thinking, how are we going to make AI systems safer? It's helpful to think about how did we make other sorts of systems safe? How did we make rockets safe? How did we make cars safe? Now, there are many lessons to think about for those specific examples of rockets and cars, but there are also some disanalogies. Safety engineering is about finding the robust analogies, what works in multiple different types of systems, and it's a collection of those. So safety engineering is a broad discipline that studies many different types of systems and provides a paradigm for avoiding accidents or catastrophes or loss events. So given this general framework of robust principles that work in many different industries for making those systems safer, we can then view AI safety as a special case of safety engineering, a straightforward application of safety engineering where we're concerned about avoiding AI-related catastrophes. So in trying to get oriented in thinking about AI safety, it's useful to be oriented by thinking about how do we make systems safe in the first place? And then we can consider some AI-specific problems on top of that. So as a roadmap, I'll discuss how we can think about risk in the first place. What is risk? And what is reliability? Then I'll talk about some safe design principles. What are some principles that are usually robustly helpful for making systems safer? Then we'll talk about different accident models, such as the chain of events model. And then we'll talk about more contemporary models of accidents. And then finally, we'll talk about tail events and black swans. So we'll start with the first section of risk decomposition and measuring reliability. Here, we will talk about how to assess and compare risks quantitatively. But first, some definitions. A failure mode is a specific way a system could fail. Meanwhile, a hazard is a source of danger that could cause harm, and a threat is a hazard with malicious or adversarial intent. As a consequence, hazards are a superset of threats. Safety is about hazards. Security is about threats. And so for our purposes, AI security is a subset of AI safety. So with the definition of hazards out of the way, we can now talk about risk. So risk is something like the expected severity. There's the probability of a hazard, and there's the severity of the hazard, and then we're summing all the different hazards. So if we consider the risk from a volcano, there's a probability it will erupt. And then there's the severity of that eruption. So what we can see is that risk is not a binary thing. It's not, do we have risk or not? It's actually a continuous quantity. So we should frame our goal for AI safety as risk reduction, not necessarily having risk equal 0. That may be infeasible. So I think it's somewhat of a confused way to frame the problem as solving AI safety or solving alignment. To see this, think about how we talk about other problems. If somebody says, we'll try and solve the intelligence problem, that sounds kind of confused in thinking. It's more natural to say that people trying to solve the intelligence problem are trying to improve capabilities, which are along a spectrum. And likewise, solving the alignment problem suggests that there is a monolithic airtight solution to be found rather than it being a continual risk reduction problem with changing constraints, changing sets of hazards, and something to progressively reduce and bring down to hopefully a negligible level. But making risk be absolutely 0 is completely infeasible. But potentially it could be brought down to a negligible or very manageable level. So let's expand this risk equation into 4 different factors. We gave the 2-way decomposition into probability and severity, but if we have some additional understanding of the problem, we can decompose it further. So in addition to probability and severity, we could consider our exposure to different hazards and our vulnerability to those hazards. Probability and severity can be tied together in this upcoming equation to be denoted the intrinsic hazard level. So here's a fuller, more detailed risk equation. Let's look at a concrete example. If we have a hazardous event H, that big Greek symbol is the summation symbol, so it just means that we're going to add overall hazardous events H. We could consider if the hazard is a specific virus or if there are many different types of virus. The risk of me being infected with a virus would mean that I'm going to sum over all the different viruses. What's the infectiousness and the virulence of the hazard of that virus? What's my contact frequency with that virus? That's my exposure to it. And what is my immunity level? Even if I get it, and even if it's harmful to some people, am I particularly vulnerable to it? So what's my immunity level? So this is another way we can think about risk more quantitatively or notionally at the very least. So for AI safety, we can think of control or alignment, but I'll tend to prefer control as the problem of reducing the existence of those hazards and their severity. And then there's monitoring, which is about if there is some hazard out there, how exposed am I to it? Can I identify it much earlier? Can I detect it? And vulnerability will be how vulnerable am I or AI systems to some of these hazards. So a system is more vulnerable if it has many potential jailbreaks. If it doesn't have many jailbreaks, then it's not as vulnerable. We can see that a decomposition of AI risk can fall out of the disaster risk equation. So having specified what risk is and given a more elaborate formulation, although the more common form is just that two-factor of probability and severity, we can turn to reliability. Let's say we're not trying to keep track of severity. Let's say we just don't want a failure in the first place. Then we don't need to consider severity. If all failures are fairly similar, then we just need to consider the probability of failure. And so this is where the notion of reliability becomes useful. Reliability of the system is the probability that an adverse event will not happen in a given amount of time. So the system's reliability depends on how often it is used. If we have an autonomous vehicle, if it's taking a short trip, it's a lot more likely to be reliable on that trip than if it was taking a cross-country trip. There's more of a risk of things breaking down because it has to make more decisions and there's more opportunities for it to mess up. Given a level of reliability, we can calculate an expected time before failure. So if the reliability of the autonomous vehicle is 50%, that is, for every decision it makes, it's either going to get it right or wrong. Half the time, it'll get it wrong. Then a mistake is likely to occur by decision number 2. However, if the reliability of the autonomous vehicle is 90%, then a mistake is likely to occur by decision 10. If it's 99%, then a mistake is likely to occur by decision 100. So you can see that these small changes in the reliability, these addition of these extra little 9 decimal points, end up increasing the amount of time before a mistake is likely to occur quite substantially. So the relationship between system reliability and the expected time before failure is not linear. This is to say that it's not that helpful to think of reliability linearly in terms of percentages. Instead, it's more useful to think about reliability in terms of its nines of reliability. So when it's 50% reliable, there are 0.3 nines of reliability. What does that mean? Well, let's just look at more examples. When there's 90% reliability, there's 1 9 of reliability. When there's 99% reliability, there's 2 nines of reliability. When it's 99.9% reliable, then there are 3 nines of reliability, and so on. So for instance, if somebody said the system reliability on a benchmark just increased by 0.9%, that could sound very insubstantial. But to a more trained ear, that could be extremely important. A 0.9% improvement in reliability, well, if it was already at 99%, then that would be very substantial. Meanwhile, if the system was just at 50% reliability, the reliability has not improved much at all. The expected time before a mistake has barely increased. But if the reliability is already very high, then it can be more substantial. So this is why downplaying small improvements to a system's performance, such as, oh, it only improved by 1%, is not necessarily the right response. It depends on how reliable the system already is. So the generalization is k equals the negative log base 10 of 1 minus p, where p is the reliability of the system expressed as a decimal. I'll make a note, which is that if the reliability is 99%, that doesn't mean that everything is solved. There's still, in that remaining 1%, there's still other issues. There's still the problem of adversarial examples, possibly. Maybe there's still some Trojans. Maybe the model just misunderstands some stuff. So I mentioned that just to give a sense of 99% does not necessarily mean that the rest is just errors in the data set. There still might be some other issues that are really hard to eradicate. So often getting an additional 9 of reliability can be quite challenging because it means you have to confront some of the more tricky problems like adversarial examples. So to recap, adding a single 9 of reliability can give a 10-fold increase in the expected time before failure. We can plot the 9s of reliability against the expected time before failure. And if we plot that expected time before failure on a log scale, you can see a nice, clear relationship. And so when we're talking about reliability, it's just more productive to think on this log scale and use the 9s of reliability shorthand than it is to talk in terms of percentage improvements. So overall, risk can be mathematically characterized. The classic risk equation is the expected severity of different hazards all put together. And if we consider the additional factors of exposure and vulnerability, then we have a more detailed risk equation, which can help structure our thinking if we have identified our exposure and our vulnerability, but it's more common just to use the classic risk equation. And then system reliability can be better measured and understood and talked about with nines of reliability rather than speaking in terms of percent improvements. Now, with that out of the way, let's talk about safe design principles. There are many safe design principles. We'll talk about redundancy. We'll talk about the separation of duties, principle of least privilege, fail-safes, anti-fragility, negative feedback mechanisms, transparency, and defense in depth. Let's start with redundancy. Redundancy is when a system has multiple backup components performing the same crucial function. So an example is there are multiple braking components in vehicles. If people store their data on multiple hard drives, if one fails, we're still fine because they're backups. And even seeking the opinions of multiple medical experts can be useful for having a system not have a single point of failure. In the context of AI, one example of redundancy could be a moral parliament of some sort. With a moral parliament, different stakeholders are voting on which ethical decision the AI should make. And this might be done automatically. So simulations of different decision makers can come into play, that these stakeholders will tend to believe that we should prioritize this good. These stakeholders will believe that we should prioritize this other good. And them working together and casting their vote together can make the system much more robust compared to if the AI system was just following one specific ethical theory. So if one theory was making an extreme assertion or one ethical belief system was recommending a very extreme view, the system will not necessarily be tugged in that direction if we have multiple different value systems represented simultaneously. This is one example of redundancy. I mean, there are other forms of redundancy, such as if we're screening the training data, we're trying to expunge some content that we don't want in it, like let's say it's toxic content or content about advanced dual use virology. We could have multiple rounds of screening with different systems, and that could make us overall safer than just relying on one. Another example is the separation of duties. So here, multiple agents work together to carry out complex processes, and each agent is specialized to a different task, so no system controls everything. With multiple system operators, the capacity to harm is reduced. As an example, let's say a lab contains 3 chemicals, which if combined explode. Well, if there's one technician in charge of all 3, then there's more of a risk. But if there's a separation of duties, if each agent is just in charge of just one of the chemicals, or there's one chemical for each agent, then we are not at as much risk. So in the context of AI, an idea is that instead of having one general AI system, we could have multiple narrow AI systems. So this is called comprehensive AI services, which is an approach that views AI agents as service providing products, each tailored to a highly specific task. This is in some ways a limitation of an agent's power by giving it a specific or a delimited purview. This is related to the principle of least privilege, which is that each agent should only have the minimum power necessary to complete their task. So what's the minimum necessary power to reliably complete one's task? This is in other areas. For instance, in computer security, you don't give the login ability or the administrator's ability to random people. Only give it to the people who need it. Only give them read permissions. If they don't need write permissions, don't give it to them. In the context of AI, we should ensure that each AI agent only has access to the information and power necessary for it to perform its tasks reliably. So we shouldn't necessarily plug AIs into the internet if they don't need to be, or give them high-level administrative access to confidential information, or give them various capabilities that are needless for their deployment context. Another safe design principle is to have fail-safes. Fail-safes are features that ensure a system will be safe even if it fails. So if an elevator breaks, for instance, there are many fail-safes. In the context of AI, they could have a confidence estimate that allows them to trigger when they're very uncertain and more likely to make a mistake. This confidence estimate could track the confidence the agent has in its decisions, and if that confidence falls below a specific threshold, then it could stop what it's doing and wait for a human to intervene. Another principle is anti-fragility. This is the capacity to become stronger from encountering adversity. This is about harnessing stressors. So an example is lifting weights. Lifting weight strains muscles, and that causes the muscles to grow stronger. Generally, complex adaptive systems tend to function better with a continual amount of stressors. Too much stasis, too much order, they tend to become more dysfunctional. Another example is infection by pathogens can result in more immunity. In the context of AI, you could have adaptive systems that continually learn online. So as the environment changes, they're responsive to those changes. This presents its own sorts of risks, though, and is not as robustly good of a safe design principle because it does create the risk that the agent will do something unexpected if it's given a looser leash and if its capabilities keep evolving second by second when it's deployed. The sixth principle is negative feedback mechanisms. Negative feedback describes processes that downregulate some types of change. So for instance, if body temperature decreases when it's too cold, there can be some negative feedback applied to being cold through shivering that helps maintain homeostasis. If one's getting too hot, one could sweat, and that would help maintain homeostasis, and negative feedback was applied. So in the context of AI, one could monitor whether an AI system is doing something wrong or a malicious user is doing something wrong and apply negative feedback. That is, one could remove the malicious user from one's platform, or in the case of an AI, have its reputation be reduced or shut it off or reset it. Another principle is transparency. Transparency is when users understand a system sufficiently well to interact with it safely. For example, pilots must understand their plane's autopilot systems. They should know how to activate it and how to override it. Model AI transparency could also help system operators steer away from different hazards, anticipate deceptive behavior, and overall have higher control over that system. Another principle is defense in depth. This is about having many layers to have higher reliability. This is related to redundancy in some ways, except that here, the layers of defense can be more distinct than having extremely similar repeats. There's often less overlap in defense in depth than with redundancy. Let's talk about the case of viral infection. There are many ways to have defense in depth. If you wear a mask or do social distancing or wash your hands, if you combine all of those, that can increase your robustness to viruses than just doing one alone. However, with defense in depth, this can introduce some unexpected consequences if there are interactions between these various interventions. So to recap, here are 8 safe design principles. There's redundancy, separation of duties, principle of least privilege, fail-safes, anti-fragility, negative feedback loops, transparency, and defense in depth. Now let's speak about different accident models. We'll discuss the traditional accident models, then we'll talk about the more modern-day systemic accident models. In this part, we'll talk about traditional risk analysis concepts. One of these accident models is the Swiss cheese model. This is very much related to defense in depth. There's getting vaccinated, washing hands, accessing healthcare, social distancing, leading a healthy lifestyle. All these things reduce the risk that a virus can make one very sick. So one can think of these arrows as hazards, and these defenses stop the hazard from going further and eventually causing damage. In the case of AI, one could have safety culture and red teaming. And if it's not found through red teaming, maybe there's cyber defense or anomaly detection, or maybe improvements in transparency help catch the issue. So having a variety of interventions can help improve safety. Let's take the example of an AI system being hijacked or jailbroken. There could be many layers of defense. There could be input filters that screen whether the request is harmful or not. Screen might fail. So there could be other sorts of interventions, such as output filters, which check whether the system's output was in some ways harmful. That's an example where stacking together these defenses can improve safety overall. And that's how one can get many of these extra nines of reliability, often by stacking many different types of interventions. I should say that the Swiss cheese model is, and in defense in depth, is useful in other sorts of industries as well. So for instance, for nuclear power, many of the individual components might fail every decade. But since there is so much redundancy, and since there are so many different backups and different defenses all working together, the reliability of nuclear power plants can get up to thousands of years before an expected failure. This is a different type of approach to safety rather than trying to have guarantees. The idea is bring the risks down to a very negligible level, make the expected time before failure be an extremely long amount of time rather than trying to have a perfect solution where there are complete guarantees. So safety can be improved by, speaking in terms of the analogy, reducing the size of the holes, reducing the number of holes, increasing the number of slices. All of those can help improve safety. Another example component failure accident model is fault tree analysis. So here the idea is to start by considering specific negative outcomes, then work backward, back chain, so to speak, to identify their possible causes. This helps us analyze some failure modes and helps us identify various hazards. This and the Swiss cheese model are helpful for doing some amount of safety engineering. It's just that it can leave out or make it harder to notice some other important factors. So let's speak about how sort of back chaining, sort of working back from a failure mode and tracing the causal steps beforehand can be fairly difficult. Let's take a look at the bottom right, for instance. Let's say there is an example, a copyrighted example in the training data that should not have been in there. Well, we could say it was the filter's fault. Well, that's possibly so. Or maybe it's because we were looking at the wrong data sources. Well, who was deciding the data sources? Well, that was the product team. Well, but the product team was speaking in interaction with the responsible ML team, and they didn't set the requirements correctly. But that's because the product team was not cluing them into enough information about what they were doing and didn't write their specification clearly enough. And because previously the training data, which was given to the responsible ML team, looked fine on previous occasions, so they didn't think that they needed to tighten up their requirements or challenge them, and so on and so on. So you can see that there's a lot of interactions between the different parts here, and putting the blame on a very specific component or the most immediate component is not necessarily going to be the most useful intervention. This chain of events reasoning that, well, this led to that, led to that, led to that, can be too simplistic or not very productive if the causality is nonlinear, if there are these feedback loops. The complex systems components may interact many unexpected ways and produce emergent properties, and accidents can happen even if no single component fails due to interaction. So we'll zoom into this limitation slightly more. The overall idea of the limitations of these component failure accident models is that causality may be diffuse, so there may be multiple factors. The events you see should not be interpreted as the result of an extremely long chain of events. You should instead view it as a product of multiple different factors. Here is an example related to the Challenger space shuttle disaster. NASA was facing a lot of pressure to perform, and it was having eroding resources. Let's just look at pressure. And I'll note that the plus and minus means that the two nodes are of the same sign. It doesn't mean additive or subtractive. It means they go together or they are anticorrelated with each other. Pressure on NASA means that there's more performance pressure. That means they're going to launch things more quickly. If they try and launch things more quickly, this makes them have a higher rate of successes. As there are more launch successes, that feeds into expectations, which increases performance pressure. So you get a feedback loop here. At the same time, NASA has eroding resources. This means budget cuts towards safety. That means negatively related a decrease in system safety efforts. A decrease in system safety efforts generally mean more launch delays, which trades off against performance pressure. As performance pressure increases, this is negatively related to the priority of safety programs. So we can see there's some complicated relations between all of these factors. It can get more complicated. If the system safety efforts are more successful, this means that there's more safety, and this means that there's an increase in the perception of safety. That means an increase in complacency, that we've been keeping things so safe for so long. Why do we need some of these system safety efforts? Maybe we're overshooting. And so that can mean a decrease in system safety efforts. So we can see that in some of these organizations, if they're doing a really good job on safety, that can actually have a pernicious effect and potentially lead to the system safety efforts being viewed as less important. I should say, though, this is just one negative feedback loop that has some unexpected consequences. That is not to say that system safety efforts, therefore, are a bad thing to have, or improving system safety or putting more effort in system safety efforts will reduce overall safety. So I have seen historically some grant makers use the excuse of we should not fund safety research because that will lead to an increase in the perception of safety, which will make people not take the problem seriously. Like, this is an argument. You can make this argument, but overall, system safety efforts are useful to do, even if a complicated, diffuse path to it is in some ways being counterproductive in some sense. On the whole, it still can be fairly useful, or it's more useful to have system safety efforts than not. And so this galaxy-brained reason is an interesting one, but not that considerable or not enough to argue why we shouldn't have system safety efforts. Let's take the Challenger space shuttle exploding. You could say it's because this thing, which was to manage heat, failed, and that's why the rocket ship blew up. You could blame it on that, or you could blame it on, well, there's a lot of performance pressure that NASA was facing, and there was a lot of eroding budgets, and these sorts of things basically fed into them launching too quickly when they didn't have sufficient safety in place. So that's viewing the result of the space shuttle exploding. That is a simple chain of events, but instead there are a lot of feedback loops going on, and there are a lot of organizational systemic factors that gave rise to or led to the ship exploding. So that brings us to these systemic accident models. This focuses on human factors and systems-based risk analysis. To give a sense of this area, I'm going to actually just read an abstract from one of the seminal papers of this space from, I believe it was James Reason some decades ago in the paper, Understanding Adverse Events, Human Factors. So I'm just quoting the abstract. This will go on for multiple slides because it's a long abstract, but this will sort of give the sense of what this area is about. One point he makes in the abstract is that human rather than technical failures now represent the greatest threat to complex and potentially hazardous systems. Managing the human risks will never be 100% effective. Human fallibility can be moderated, but it cannot be eliminated. So here there's a view that we're not looking for perfect solutions. We're just trying to make sure that errors don't cascade into catastrophes. Then he says significant errors occur at all levels of the system, not just the sharp end. So he's making a sharp end, blunt end distinction. The sharp end are the specific individuals involved, the specific technology involved, rather than some of the blunt end type of factors like what's the safety team's budget, what's their performance pressure, what's the understanding of the problem by management, do they get it, are they supportive, etc. Decisions made in the upper echelons of the organization create the conditions in the workplace that subsequently promote individual errors and violations. So here's talking about diffuse causality from the higher levels of organization. This can flow down into errors into the individual system. Latent failures are present long before an accident, and hence prime candidates for principled risk management. So rather than looking at immediate types of failures, that this component failed, had a bug. Instead, this is trying to get at some of these latent failures that aren't necessarily manifesting themselves immediately and trying to intervene on those. Measures that involve sanctions or exhortations, that is, moralistic measures directed toward those at the sharp end, have only very limited effectiveness, especially in the case of highly trained professionals. So let's say because the space shuttle blew up, we're going to blame one of the coders. There was a bug in the program that if it was fixed, it never would have blown up. That could be a way you try and perform risk management, just chewing out your employees. That's not going to be very effective. That's not actually going to fix anything. The larger factor was there's really high performance pressure and there were budget cuts. Telling them not to write buggy software is not an actual solution because every human who codes will write buggy software. An additional thing James Reason notes in this abstract is that people do not act in isolation. Their behavior is shaped by circumstances. The same is true for errors and violations. The likelihood of an unsafe act being committed is heavily influenced by the nature of the task and by the local workplace conditions. These, in turn, are the product of upstream organizational factors. Automation and increasing equipment do not cure human factors problems. They merely relocate them. Effective risk management depends critically on confidential and preferably anonymous incident monitoring system that records the individual, task, situational, and organizational factors associated with incidents or near misses. Effective risk management means the simultaneous and targeted deployment of limited remedial resources at different levels of the system, the individual or team, the task, the situation, and the organization as a whole. So this is a much broader view of how to go about risk management, how to think about what it gives rise to accidents and catastrophes that moves beyond this event led to that event, led to that event, and everything worked like a clockwork, one domino tipping over the next. So this view is more socio-technical in nature. Typically, people will think about the operating processes. So AI safety in the dark ages would largely just think about this problem, which is how do we make the AI system safe? That's not actually how we're getting about risk management. This is one part of the system, but we have to think about other sorts of things. We have to think about the operations of the operators of those systems. We have to think about the companies that make or that employ those operators and make those systems. We have to think about the regulations that shape those companies. We have to think about Congress and branches of governments that require agencies to create standards. So we can see the government influences regulators, which regulate the company, which regulate management, and that affects the frontline workers and the actual work. And these all feed into each other. So there are feedback loops between all of these different parts of the system and these different levels of organization. So in thinking about risk management, and if one's just trying to approach AI safety from a safety engineering standpoint, it is wholly insufficient just to think about the AI system directly or solely. One needs to think about all these other levels of organization, and this requires a lot of breadth. And this is why I think AI risk and AI safety is a difficult issue for people, because many of them come in with just a technical background and know a lot about AI and try and think, how are we going to make AI safe? How are we going to make sure that there are no societal risks? Let's try and answer that problem just by tinkering with this system right here. And we'll just leave some other quote unquote governance people to think about this other sort of stuff. But unfortunately, we have to think about the entirety of the system. We can't forget the company management. We can't forget the regulators, and that these groups need to speak with each other. If we are going to do comprehensive risk management, they can't be siloed. Some people can't just be working with Congress, and some people can't just be working on the AI systems. We need people to be making sure there's appropriate information flow between all these different parts. And we especially need places like Congress not to assume that the only thing to do is to let AI people figure some sort of stuff out. There's much more to system safety than just intervening over here. Intervening on all parts of this socio-technical hierarchy is more comprehensive risk management. Here's another systemic or system level accident model. It's to say that we can get in the unsafe region given various different types of pressures. There might be a pressure for efficiency. There might be a pressure toward putting in less effort. And these together can make the system overall less safe. Then we can drift toward failure. This model is basically saying it's not as much a chain of events in particular. There's some systemic conditions that cumulatively make the system tolerate failure more and eventually make the system drift into a critical state. This model is one reason why it is useful to address ongoing hazards, not just focusing on existential risk. Because if you normalize catastrophes, that can make the system drift into a more critical state and makes various even more dangerous states more likely. The system theoretic accident model and processes, or STAMP, also incorporates this drift into failure type of model. It adds a little more color. STAMP says that safety is an emergent property of a system, not the product of all the components behaving reliably. Reliable systems are not necessarily safe. A system reliably making a bioweapon is not necessarily safe. A nuclear weapon may be reliable, it is not necessarily safe. STAMP also says that a system contains multiple levels of organization, and each level has novel emergent properties that need to be considered. And we cannot understand the emergent properties of a given level through a reductive analysis of the level below. Obviously, I'm speaking at a 30,000-foot view here. We'll speak more about complex systems in the next lecture, but it's being explicitly about complex systems here, since it is saying that we need to consider emergence. Safety is an emergent property. It's not found in the parts. Having a system be completely adversarially robust does not make it safe. Having a system completely obedient to a person does not make the AI system necessarily safe. It requires a combination of various different things going well, and even then, if they're all performing reliably, it depends on how they're interacting too. STAMP also says that safety can be enforced with each level placing constraints on the level below. This is an approach of controlling complex systems in a top-down way. STAMP-based risk analysis involves modeling four system aspects: the organizational safety culture, the dynamics and pressures that can deteriorate safety culture, the necessary operator knowledge and communication about processes, and the cultural and political context of decision-making processes. So much more holistic. Does management care about safety? Do the individual employees, do they care about safety? Are they always on guard? Are they thinking about risks? Is there pressure tugging them not to? What are the constraints that the operators face? And also at the high level, what are the types of regulations that they're facing, et cetera. So I'm not describing STAMP in complete detail, but this is just to give a sense of some of the claims that it makes. Some additional claims can be appreciated through a juxtaposition. So in component failure accident models, those sorts of models will often say that accidents are caused by a chain of directly related events, Meanwhile, with STAMP, it's saying that it's more productive to think of accidents that are complex processes involving the entire socio-technical system. So much more holistic. A prior assumption, or an assumption of some of the non-systems based models, is that we can understand accidents by looking at the chain of events leading to the accidents. Meanwhile, STAMP is saying that this can miss many important hazards, and while it can catch some, it won't catch many of the things that we care about. An old assumption is that if we have everything behave reliably, then everything is perfectly safe. And STAMP is to say that safety is not equal to reliability. I gave some examples of unsafe reliable systems. A safe unreliable system would be, I don't know, maybe a Tamagotchi pet. And let's say it has a bug, its battery is inconsistent. So it's not reliable, but it's safe. Most accidents are caused by operator error is an old assumption. So blame the operators. If the plane crashed, it's the operator's fault. It's not the company's fault. Meanwhile, this recognizes there's a variety of factors that could have led to a plane crashing. And it's not necessarily the operator who's to blame. Maybe it was actually the software, and maybe that's because they were trying to rush out a new product because Airbus was being more competitive. Assigning blame is necessary to prevent accidents. Meanwhile, STAMP is saying blame is a very common thing. It gives us a feeling of control, but yelling at the frontline workers is not necessarily the most productive way of reducing risks. The old assumption is that major accidents occur from simultaneous occurrences of random events. Instead of that, this is more this drift into failure type of model, which is that systems tend to migrate towards states of higher risk. A combination of various pressures lead them to be more prone to a catastrophe through the normalization of various smaller scale failures. So to recap, AI safety can be viewed as a safety engineering problem. The component failure accident models provide insight in how to prevent individual errors and their knock-on effects. We discussed the Swiss cheese model and fault tree analysis, which used a sort of implicitly a chain of events type of model. Meanwhile, the system accident models takes a more holistic view and considers how to make the entire system safer rather than a focus on the direct interactions between individual components. It'll focus on more things like feedback loops. And so finally, we've discussed various ideas from safety engineering. Now I'll add a question mark behind some of them, or a kind of critique, an asterisk, a limitation of the preceding analysis. It's not to say it's all to be discarded, but one thing that makes risk management substantially more challenging would be tail events and black swans. A tail event is a low probability but high impact event. And a tail risk is the possibility of a tail event with negative impact or negative severity. This is related to a black swan. These are tail events that are unanticipated. They are unknown unknowns, which is something we'll discuss later. One quote that can help give the idea of what we're talking about is that things that have never happened before happen all the time. So when proceeding with risk management, it's important to approach it with some level of humility. Some example of tail events would be the 2007 financial crisis, or the COVID pandemic, or ChatGPT. Here's a caricature from, I think, Taleb's The Black Swan, between tail events, thin tails, he's calling these events that are not tail events, and then long tail events are these actual tail events. So these very minor events, or the situation where minor events dominate, and the right column is when tail events dominate. So at the left, top few receive a proportionate share of the total. Meanwhile, for long-tailed situations, the top few receive a disproportionately large share of the total. I'll skip down to a single event cannot escalate to become much bigger than the average. Meanwhile, in these more extreme scenarios where there are more tail events, a single event can escalate to become much larger than many of the events put together. So for instance, AI could be viewed as a tail event. It matters more than a lot of other sorts of events going on. It matters more than probably everything that will go on in Hollywood, for instance. It matters more than the goings on of various sorts of industries. The last point, we can predict roughly what value a single instance will take. Meanwhile, with long tails, it is much harder to robustly predict even the rough value that a single instance will take. So with tail events, there's substantially more unpredictability. And we discuss this in more detail in the book and break these down and give more concrete examples of long tail events and thin tailed events. So this sets the stage for talking about black swans. Black swans get their name because some Europeans thought that all swans were white, but then they observed a black swan. And then this made them redefine how they thought about swans and caused them to reassess their worldview. So black swans can do that. Black swans are tail events that are largely unanticipated by most people. So for instance, the financial crisis in the 2000s was a black swan event, except to a few people who actually predicted it. But by and large, it was a black swan event. Pandemics to many people are black swan events, but to people who are following it more closely, they were fairly prescient in February. But to most people, it was a very substantial surprise. An important concept to think about black swans is the concept of meta-ignorance, which is encapsulated in the phrase unknown unknowns. So black swans are, to most people, unknown unknowns. So what are these different terms? What's an unknown unknown? It's when you don't know what you don't know. Let's contrast it with some of these other concepts of known knowns. Known knowns are things we are aware of and understand. They are specific facts that we know, for instance. Known unknowns are things we are aware of but don't fully understand. These are closed-ended questions. This is things like, what will the temperature be tomorrow? Unknown knowns are things we do not realize we know. These are explicitly known. This is tacit knowledge. We may have a gut reaction of, this doesn't feel right, but I can't really articulate why. Maybe it is wrong, maybe it isn't, but there's some underlying knowledge being tapped into one's representations that one doesn't fully articulate or even know why one is responding in that way. So a lot of know-how will be tacit knowledge when one would say, no, that's just not how you do it. That's clearly wrong, but I can't quite say why. That's where there are more unknown knowns, and a lot of academic work is trying to turn those unknown knowns into codified explicit knowledge into known knowns. And then unknown unknowns are things we do not understand and are not aware that we do not know. And these can be encountered through things like open-ended exploration. So if something is off our radar and it's not even a consideration we thought to raise, that would be an unknown unknown. So now let's talk about another concept in thinking about black swans in a more informal way, is with the turkey problem. After a comfortable life at a farm, a turkey is suddenly killed and eaten. From its perspective, this might be a black swan. This example is popular because it would illustrate that if the turkey was just keeping track of each day, it would think, I'm being fed every day, everything is fine, the farmer must care about me, it keeps feeding me, and the next day it's the same thing, and so on and so on. And if we took the average, if we did a statistical mean, if we used basic statistics, the turkey would think tomorrow is extremely likely that everything will be fine, and given the past, everything will continue to be fine. This is relevant because if it's a black swan type of event, prior statistics do not necessarily predict the future. So it suggests that relying on historical track records aren't necessarily enough to discount black swans. One could say that this could be potentially analogous, maybe, maybe not, for the context of AI, where we've had a lot of consistent economic improvements, roughly speaking, overall, since the Industrial Revolution. We could think that there's a continuation of that. This is sort of exemplified in the book Enlightenment Now. Things will just keep getting better and better. Maybe you're actually in for a series of events that could really disrupt that trend. So some black swans in AI, black swans to most people, maybe they're gray swans, they're things that are on our radar, but we really have not wrapped our head around. Regardless, they function still fairly similarly. If AIs are sentient or have well-being and are morally valuable in the future, this would really disrupt our relation with AIs and how we think about the future of AI. If we have a fully autonomous economy, this is also something that would rupture most of our ontologies and how we think about things and would require substantial reorientation. Likewise, extremely compelling embodied AI companions could also change the game and change the human condition to become nearly unrecognizable. So some implications of black swans for risk analysis are as follows. One implication is that typical risk estimation breaks down. We discussed how with tail events, it's fairly difficult to estimate their probability, and it's fairly difficult to estimate their severity. Whereas with other sorts of events, we can often get more robust estimates. It's not necessarily the case here. Relatedly, cost-benefit analysis breaks down. Just as an example, let's say that there's a lottery with a $15 payout at 99.9% probability, but otherwise you lose $10,000. This still may be a positive expected pecuniary value or positive expected monetary value lottery. But if the estimates change just slightly, then it becomes very negative. So when doing cost-benefit analysis, in the case of long tails, small changes to one's probability estimates, and there's a lot of uncertainty behind those probabilities, can really mean that one wants to not just choose things that are positive in expectation, but instead do things that are robustly good. such that small changes to the conditions or a slight increase in the presence of some tail events or black swans, one should be robust to those small changes in one's model. So for black swans as well, estimating the probability can be more challenging. It might not even be on one's radar. I suppose by definition for black swans, that would be the case. If they're gray swans, they could be on one's radar, but still could be a very novel event for which assigning a probability would be very difficult. So this is how some of these traditional risk management concepts can strain further or be less reliable than before. In considering black swans, it's important not to be more skeptical of statistics generally or running averages, things like that. If one has calculated a historical risk level, that's not necessarily sufficient. One example of how we shouldn't just rely on some, average statistics for things is never try to walk across a river just because it has an average depth of 4 feet. There's more structure we need to be considering than historical track records when confronting black swans or when trying to be robust to black swans. Another implication is the delay fallacy, the idea that we should delay making our decision to gather more information. This is a good idea in very typical situations, but is a bad idea when dealing with black swans in many cases. So in long-tailed scenarios, waiting for more information can mean waiting until it's too late. In the case of exponentials, you're either too early or too late because it grows so quickly. You're either on the early side or the late side. Being timed exactly right is very unlikely, extraordinarily unlikely in the case of exponentially changing targets. So with black swans, waiting may yield no useful information at all. Large-scale black swan events should not even be allowed to happen once. If you wait for more information, you might be waiting for the sudden shock or the sudden event or catastrophe to happen, in which case the information is not useful anymore because the catastrophe has already happened. So one's typical scenarios that work for more standard scenarios require one to be more precautionary when dealing with potential tail events. Relatedly, an absence of evidence is not strong evidence of absence in the case of tail events. Instead, an absence of evidence is evidence of absence in proportion to the evidence that one would expect. So in the case of a tail event, we wouldn't necessarily expect to observe that tail event until it actually happens. All the information may come in a lump. So the fact that it hasn't happened yet is not necessarily strong evidence that it won't happen. For example, saying, why would you expect there would be a financial crisis? Well, I haven't seen a financial crisis yet. Therefore, there will not be a financial crisis. That's not necessarily a good argument because it will happen potentially very suddenly. This isn't to say that people can then proceed evidence-free because, well, although I don't have any evidence of it yet or particularly strong evidence of it yet, that means you have to listen to me. So arguing in that direction could prove a bit too much, but this does mean that one should proceed in a more precautionary manner, but of course not try and be over-responsive to any potential risk scenarios that anybody could mention or imagine. Another implication is the preparedness paradox. Safety measures that successfully prevent harm can seem redundant. We sort of saw this in that feedback loop earlier in this presentation, where if the safety teams have been so successful at reducing risks, one might think, why do we need the safety teams? I haven't seen any risks in a long time. So if one has not been sick yet, then one would think, I don't need any of these safety interventions. So this is a pernicious problem to be aware of in engaging in risk mitigation. So to reduce these sorts of tail risks, one robustly useful thing is this horizon scanning thing. Find potential black swans, get them on your radar, turn them into known unknowns from unknown unknowns. Now you're at least aware of them. There's still substantial uncertainty, but then one can try and improve one's understanding of the problem. Another thing is use interventions that have been robustly useful in many different sorts of contexts. So incorporate safe design principles. Another important thing to do is to improve systemic factors such as risk awareness and safety culture and attentiveness to near misses. Reduce one's exposure to risk and follow the precautionary principle. Although we may not have an extremely precise estimate of the risk, we can still reduce our exposure. Fairly commonly, people say what we should do now is we should try to get a more precise understanding of the risk before acting. That's basically that delay fallacy. When instead, if there's low-hanging fruit, if there's obviously robustly useful things for reducing our exposure to risk, and if that's cheaper than doing a long scientific excursion into, getting a more precise estimate, just reduce the exposure to the risk. Often modeling these sorts of events can be fairly difficult. There might be a lot of tinder or hazards that could potentially become inflamed or cause an accident. So just remove that tinder. We don't need to build up a sophisticated model of how exactly does that lead to an accident and with what probability down to 2 decimal points. Other useful things are improving the epistemics of decision makers and improving institutional decision making. Having them just understand this AI problem, for instance, is robustly useful for not walking into tail risks. And another intervention is changing researchers' incentives. Make them have skin in the game. Make them internalize their externalities. Don't let them just get the benefits of AI while at the same time not absorbing or having any responsibility over the risks. So if something bad happens, there's a risk of them facing negative consequences. That can fix their incentives and make them not be so cavalier about risks, and is a way of improving systemic factors. Beyond prestige boosting safety inside of one's organization, having some of them be on the hook for disasters or harms that they cause is another way of reducing tail risks. So to recap this section, tail events are low probability but high impact events, and tail events render common statistical measures such as expected values very unreliable. Consequently, it's not enough just to look at whether the cost benefits are positive or negative. One should instead take interventions that are more robustly useful. And we spoke about many other sorts of interventions one can do to reduce tail risks. Black swans are unknown unknowns. Unknown unknowns are things that we don't know that we don't know. And with dealing with black swans, we can inherit many of the ideas from safety engineering, such as safe design principles, such as improving systemic factors. But there are some other things that are useful, such as horizon scanning, trying to put